Hello and welcome to Miles to Go. I'm Miles O'Brien. On this edition, the most important greenhouse gas you might not be worried about. I'm talking about methane. It's less long-lived than CO2, about a decade or so, as opposed to at least a century for CO2. But it is also much more potent. At the bottom of the ledger, it's responsible for about 1/5 of the global warming we are experiencing right now. According to the EPA, about 1/3 of methane emissions come from oil and gas production, another third from the belches and manure that come from livestock as part of our dairy and meat production enterprise. And then about 16% comes from the organic waste that we dump into our landfills here in the U.S. If you want to know more about that, by the way, check out Miles to Go, episode number 2. It's called Talking Trash, and our guest in that one was Eugene Sung, who is an expert on these matters, and he offers a scathing indictment of our trash habits in the U.S. They have a big impact on global warming, believe it or not. But back to this podcast. Our guest on this episode is Robert Green. He is a fellow at NASA's Jet Propulsion Laboratory, and that's a big deal, by the way. He's a world-renowned leader in the world of imaging spectroscopy. Now, that's an important tool at identifying all kinds of things in deep space, like is there methane on the planet Titan, for example. But it's also good when it's pointed at our own planet. It gives us a chance to see what greenhouse gases are in our atmosphere, what quantities there are, and where they might be coming from. You've spent 30 years in this realm looking at how spectroscopy can help explore the frontier. Just give us a basic idea of how spectroscopy helps you in space, first of all.
Okay. In space, we're almost always in the position of trying to decide what something is without being able to touch it, the rovers being exceptions. Spectroscopy lets us measure photons that have interacted with matter and look at that interaction through wavelength and look for the spectral fingerprint or the signature of those molecules, methane being one example, and know for certain we've got methane occurring at that location. On the planet Mars, we used spectroscopy to decide where to land the MSL rover. Where was an interesting place where there was a range of rock types, and there's a spectrometer currently in orbit around Mars. In space for the moon, we had questions about what is the mineralogy of the moon. Minerals are different molecules. They have different spectral signatures. We built an imaging spectrometer and sent it to the moon. In addition, discovered that there was water in the soils of the moon under illumination, which was not expected to occur. So those are examples of the powerful way NASA uses spectroscopy to push the frontiers, to test hypotheses, to answer new science questions.
Spectroscopy as a field of endeavor to do what you're talking about is how old?
Spectroscopy really was conceived by Fraunhofer in Germany in 1814. He invented the spectroscope. He wanted to understand the composition of certain glasses to build better telescopes. Soon after that, he collaborated with Kirchhoff and Bunsen, and they noticed that the spectral lines they were seeing in the laboratory with Bunsen-Burner-like processes had the same locations in the wavelengths as part of the sun. So they were able to deduce that the sun was made of some of the same compounds and elements that they were seeing emission lines for in the laboratory, as an example. So really, the first spectrometers grew out of that early work by Fraunhofer in Europe.
So we're talking early 19th century. Scientists using this technique were able to tell us quite a bit about what the sun is made of.
Exactly. And Edwin Hubble, who understood here adjacent to JPL from Caltech, he discovered the Big Bang. He used that by looking at different stars and looking at their spectra and noticing as they got further away, there was a shift implying in the currents of spectral absorption lines, implying that the universe was expanding. That's another example of how we've used spectroscopy.
And in current day, it comes into play quite a bit as we build the catalog of exoplanets, right?
Exactly. Now we have more than 1,000 planets orbiting stars through our galaxy, and the light that's coming from those planets sometimes The starlight is reflected from those planets. That light then arrives at the Earth. And if we look at it spectroscopically, we can say something about the composition of those planetary atmospheres. Currently, with Hubble, we've already shown that there's water, methane, and carbon dioxide in some exoplanet atmospheres. And there's a host of new missions, including NASA's JWST, that will take us much further in understanding the composition of those atmospheres and looking for disequilibrium chemistry, which might be an indication of some very unusual processes.
So let's do a little bit of spectroscopy 101.
Okay.
Basically, we're talking about how light passes through gases, and depending on what it is and how it interacts, it has a distinct, squiggle of lines.
Fingerprint or signature.
So walk us through that. Explain it, if we could, to the layperson.
So light, in this case, we'll say emitted by the sun, arrives at the top of the Earth's atmosphere. As it passes through that atmosphere, there are certain wavelength regions where water vapor absorbs the energy. So it leaves a gap in that part of the spectrum compared to the spectrum that arrived from the sun. Carbon dioxide and methane also have their region of the spectrum where they take some of the energy out. And then if we observe that spectrum, we know what the source looks like from the sun. We see what's missing, and those fingerprints or signatures, this is absorption spectroscopy, tell us those molecules are present. And based on the strength of those signatures, we can quantify how much is present. And that's what we're currently doing with the methane mission, flying with the AVERIS next-gen imaging spectrometer.
So just one thought comes to mind, though. If the atmosphere is taking pieces out of the spectrum out for you, how much does that inhibit your ability to see beyond the atmosphere?
To see the surface properties,
yeah,
for example.
If you're looking at a distant planet,
yes,
and you're being filtered by the carbon dioxide, water vapor, all those things in our atmosphere, do you just have to know what you're missing first before you look out there? How does that go?
Most of the key exoplanet and planetary work has to begin with spaceships that are above the Earth's atmosphere, and that gets you past that problem. There is an interesting twist in the sense that there's a Doppler shift in absorption lines as a function of how fast the object is moving. So since exoplanets are moving at a different rate than our atmosphere, there's slight shifts in those absorbed. Same molecule, methane in both cases, but slight shifts in their locations. So that's some of the leverage we can use to try to work through the Earth's atmosphere. But it's much more straightforward to be above the Earth atmosphere when you're looking at other objects like exoplanets or other planets in our solar system.
Is there any doubt in your mind that when the day comes, spectroscopy will be the first indication of life somewhere else? I'm
very hopeful that that will be the case. Spectroscopy certainly is a player for making the case that life is occurring. For example, in an exoplanet, establishing disequilibrium chemistry, seeing oxygen, making maybe the case that there was some molecule like chlorophyll, would be examples of what spectroscopy could do to help us make that case that there might be a life process occurring on another planet.
All right. You're not going to, you never say.
I'm a scientist,
You're a scientist.
right?
You can't
I
do
can't.
that. You physically
my life is
can't say that word.
Falsifying hypotheses.
No doubt would be like,
everything is tentative.
Okay,
falsifying hypotheses. That's what I do.
Let's move, just before we get into AVERIS and explaining how it works, what's the problem with methane? Why is it a challenge to detect?
Methane is a molecule that occurs naturally in the Earth's atmosphere. It's also released by anthropogenic or human processes. It has an absorption signature that's in a tough part of the spectrum. The signal that we would use from the sun is starting to fall down at those wavelengths. And then in some regions, the other signature we would use isn't really available because the Earth is quite a cold planet by comparison. So it happens to occur because of its molecular nature. It's carbon with 4 hydrogens. The absorptions that occur from that molecular structure occur in a wavelength range that's quite challenging. So we've had to bring the very best instrumentation possible to bear to try to measure it, and that's what we've been doing with the recent California methane experiments.
Is there a layperson's way of explaining that a little further when you say, or is that's a tough one, right? I mean, you're in a tough part of the spectrum.
Yes.
Because, I don't know, maybe this is too much detail, but do you want to give it a whack?
Sure.
Yeah.
So for some molecules, like oxygen in the Earth's atmosphere, they occur in a spectral range where there's lots of sunlight, and we can see that signal absorption of oxygen very easily. But it turns out methane is occurring at longer wavelengths where there's less energy from the sun, and so we have to have the very high quality instrument to detect a much weaker signal comparatively. And that's just the nature of that molecule it doesn't absorb in the regions where we have a lot of signal to work with, for example, where the sun is peaked.
So I'm sorry, there's less energy for the sun, meaning, no, the sun is, the energy of the sun remains the same.
As a function of spectral range, that the sun has its maximum output near the 550 nanometer wavelength, the green and the visible. And as you go to longer and longer wavelengths, there's less energy in those longer wavelengths. And it turns out methane absorbs in those longer wavelengths where there's less energy to work with, requiring more sophisticated instrumentation.
How does AVRIS take the science of spectroscopy to a different level?
So there were the point spectrometers of the 1900s. In the late 1970s, it become apparent that the technology was arriving. There would be detectors, optical designs, and computer processing that could allow you to build a whole new class of instrument, an imaging spectrometer, an instrument that collected images, but a spectrum behind every point of that image. Before, there had only ever been point spectrometers. And those ideas came together at JPL. And they caused us to build the very first spectrometer called AIS. It had that 32 by 32 element, the 1K pixel imaging spectrometer. And that flew in 1982. Because of its immediate success, we then proposed AVRIS, the Airborne Visible Infrared Imaging Spectrometer, which is far more capable. That began flying again early in the 80s, and now we've built AVRIS Next Gen. These instruments were invented here. They have this unique characteristic. They collect spectacular images, but there's a spectrum for every point of that image that allows you to then map the molecules, not only measure how much is there at each point, but then build that spatial image to give you the spatial context and answer the more challenging questions.
So you're a long way from that 1K thing.
Yes.
But the idea of pairing image and spectroscopy, why is it? I mean, that seems like, of course you'd want to do that. What was the limitation previously to that idea?
Previously, the detectors didn't exist. The computers couldn't begin to handle the sort of data volumes that arrive. And the designs, it turns out that we needed new designs of spectrometers that weren't just point spectrometer. It didn't just make one spectrum, but built a whole image of spectra and put that properly on a detector area array, like the area array in your camera.
So is this what we call mass spectrometry? Is that the difference or not? No?
No, mass spectroscopy measures mass instead of wavelength.
Oh,
so it's the amount of mass on the x-axis and the abundance of it. It's a dispersion process, but instead of dispersing light, you're dispersing the mass of particles. And it's a very powerful analog tool, but only relevant really for in situ measurements. You have to have the thing, and you're going to disperse materials.
So try to give us an idea of how, from 1982 to your current iteration of AVRIS, the next gen, how much things have improved.
So it's quite extraordinary. I've learned new words. Now with AVRIS Next Gen, I've learned the word petabyte. It's not a terabyte. It's not a gigabyte. 1,000 gigabytes is a terabyte. 1,000 terabytes is a petabyte. Those are the sorts of data volumes we're collecting and processing to answer these new questions with AVRIS Next Gen. We also have detectors which are far more sensitive, letting us see methane in ways we never could with those detectors of the 80s and 90s. So those would be key areas. Also, our optical designs have evolved and are continuing to evolve to the point we're now ready to take an imaging spectrometer of the AVRIS class to space to look for methane globally and make contributions in that area.
Is methane the prime target for AVRIS Next Gen? What other applications are you after here?
It's a wonderful question. AVRIS Next Gen is a very multi-purpose tool. We use it to look at ecosystems. We map biodiversity. We've mapped the forest fall-off in California due to the drought, the senescence of the big trees, for example. My colleague Tom Painter uses spectroscopy to look at snow in the mountains of Colorado and California to make predictions about the runoff. Geologists use it to look at where different minerals are. As we did with the moon, we can do that on Earth with the different minerals. We just finished a major NASA mission called CORAL, the Coral Airborne Reef Laboratory, which flew an imaging spectrometer to the Great Barrier Reef, to Hawaii, to Palau, and Guam to map the characteristics of corals in ways that have never been done before and answer new questions about the status of coral reefs and what's impacting them, whether it's temperature, acidity, human impacts, wave action. So that mission would be another mission. So water, geology, atmosphere, ecosystems, snow and ice, wildfires. It's a very powerful capability because it can measure a spectrum for every point in the image.
Is it accurate to say it is uniquely capable at detecting methane?
There are other methods to detect methane, but it is uniquely capable in this mode of large surveys. We're collecting 60,000 spectra per second. You asked how things were different in the 80s. 60,000 spectra per second is extraordinary. When I was in university and using my Beckman spectrometer, it took me a minute to collect one spectrum. So that's what AVERIS offers, this ability to multiplex spectroscopy and cover large regions in the state of California. And that's why it's really ready to go to space and begin to answer the big questions about methane point sources in particular with this technology.
Did you have to optimize it in some fashion to dial it in for methane, or was it kind of off the shelf ready for that?
It really was off the shelf ready for that. In fact, it's a surprise. We actually broke a paradigm. There were a number of atmospheric spectroscopists who are used to working at very high spectral resolution who didn't think we would be so successful. So we did a series of tests and showed that AVERIS, even as originally invented, was really quite a powerful tool. The changes we have made to AVERIS Next Gen for methane is we put a real-time algorithm on the instrument. So the operator flying along on the airplane can see the methane plumes as they're detected, adjust their brightness. And one interesting case in Chino Hills, in a residential area, we saw a large methane plume. It wasn't supposed to be there. So we called in Southern California Gas. They went out there and said, yes, there's a leak in one of our methane lines. And they shut down the line and they repaired it. So that was a very fulfilling result, and how we used that new real-time capability to make a decision with value to people locally.
SoCal, I think they'd like probably to acquire JPL at this point. They're pretty happy with what they're getting from you guys. What's that partnership been like?
It's been very fulfilling. The AVERIS Next Gen team, there's nothing more exciting to make a positive contribution for people in understanding the process of methane leaks, and in fact finding leaks where their homes might be at risk. So it's been really fulfilling. And we've made a number of discoveries. We've broken some beliefs. There was a number of areas in the San Joaquin Valley where it wasn't understood where the methane sources were. That was known to be a methane high in a general area, but because we could see the methane in the image, we could describe this landfill is actually leaking here. And if you made these changes to that landfill, you could reduce the methane. You could burn it to reduce its effect as a greenhouse gas, for example.
Just a quick word on that, because I suspect people won't think of this. If you take the methane and burn it, the derivative would be CO2.
Yes.
Are you better off? Because CO2 stays in the atmosphere so much longer. It's less potent. What's the math on that?
I think the math still remains that methane is more potent and more serious. So you want to get rid of the methane if you can, and one of the options to let it go to CO2, it would be better if it didn't occur in the first place, but that reduces its next heating effect in the atmosphere.
I get the sense sometimes that we've been focusing on the wrong greenhouse gas in some respects. Would you agree?
We need to focus on the full range of contributors, and there are methods to do that. It turns out AVERIS Next Gen also measures carbon dioxide quite well, maybe not quite as well as methane. But so this tool of spectroscopy can make a contribution in understanding both CO2 and methane point sources for us to make decisions about how we want to address those.
So you've been painting a rather detailed portrait of where the methane is. What's been the biggest surprise?
Well, I think in some cases, some of these landfills were leaking more methane than people realized. Some of the digesters, which are meant to take manure and let bacteria convert it to a product that doesn't release methane, have been releasing more methane than expected. And we've even been able to see some regional plumes of methane, which wasn't expected that AVERIS Next Gen would have the sensitivity where it could fly a series of flight lines in a big racetrack and then look at the methane and see this broad bubble of methane that might be coming from sources in that region. So those are some of the surprises, plus the initial surprise that we would even be this sensitive and this effective in the first place.
Put Aliso Canyon into the mix. What was Aliso Canyon? Must have been, from a scientific perspective, kind of a Super Bowl for you guys.
Yeah, it was an extraordinary opportunity to test our sensitivity and whether we could see methane with this detection methodology. So we were very fortunate. NASA funded us to fly AVERIS, the original AVERIS, in the ER2 at 65,000 feet over the Aliso Canyon methane plume on 5 different occasions, and we could monitor the whole plume shape, where it was going, and the abundance at that time at each point in the plume. And then finally we flew it after it was declared shut off to verify it was off. It was one of the verification tools to show that the leak had been plugged. The other really neat story is I was sitting at the American Geophysical Union in 1915, and my colleague from Germany, Louis Gunther, said...
No, 1915. You
sorry,
were...
sorry.
2015. You look like $1 million.
In 2015.
Yeah.
And the idea of methane with a spectrometer was being discussed. And we realized there still was a spectrometer in Earth orbit that might be able to see the Aliso Canyon plume. It's called the EO1 Hyperion spectrometer. It was in its 15th year of operation in Earth orbit, and it had drifted to an orbit that wasn't so optimal. So I made the call to my friends at Goddard. They pointed EO1 Hyperion at the Aliso Canyon, and we made the first ever detection of a methane plume from Earth orbit. And that was another example that the Aliso Canyon allowed us to test the algorithm and the viability of a future spaceborne approach to pursue methane point sources and CO2 point sources as well.
So I imagine you have a pretty good degree of confidence. I wouldn't say it's undoubtedly so, but a good degree of confidence that if you could get the next generation of Avarice in space, we could really get a big picture of the methane problem, perhaps globally even.
Yes, I think that's something that Riley Duran and others at JPL, myself included, are working towards, to show we have the algorithms, we have the airborne test case, we think we have the detectors and the designs, and we're trying to pull that all together to what might eventually be a constellation of small sats that would allow us to revisit areas every few days and assess local methane point sources and help people make decisions how to manage those. So I think we really are right now ready to take that next step, and such constellation could be flying hopefully in the near future.
It's interesting that there's that much methane that leaks all around us when you consider this is a commodity that can be sold.
I agree. And I think that's another fulfilling thing for us. When we find a leak, the gas company's very happy to know they have a leak, because then they can fix that leak and charge people for the use of that methane. So I agree, it's interesting how there are more leaks than people expected, and maybe we can turn that to our advantage to capture it and use it for fuels in this intervening period where we're using more methane than other fossil fuels.
NASA's Earth Science Enterprise faces, budgetary concerns, to say the least. Make the case for it.
We can provide information that's valuable for policymakers to make accurate decisions. That's one of the great contributions. And it's not just with the atmosphere, but it's with ecosystems, it's with biodiversity. It could be with agriculture. It could be in the area of mining and applications. Understanding the nature of urban surfaces, for example. So there's a whole host of important contributions we can make that can allow policymakers at the national and state level to make better decisions, decisions based in evidence.
That's a nice thought. Good luck with that one.
Well, I have my I'll tell you my 3 E's: evidence, excellence, ethics, and excellence. Those are the 3 E's I look for.
We're lacking in all 3 at the moment.
I didn't say it. I didn't say it.
Don't worry, I won't get you in trouble,
Thank
guys.
you.
It's all right. Are you reasonably hopeful that methane is a problem that can be addressed in a meaningful way?
Yes, absolutely. I think we're already doing it in a case-by-case study with this example, and I'm sure there are other examples where that's being done, where you can find a leak and you can fix it. And as you said, it's low-hanging fruit, because when you fix it, you can turn the methane into money. Absolutely, I think methane is something we can make a contribution, and NASA's technology can make a contribution towards reducing the methane and turning that methane into the value that the people can sell.
Given the bottom line incentive here, is it possible this is a problem that could take care of itself once you identify where the methane is? Will it, by virtue of the fact that it has value, go away?
I don't know. That's a question for economists. It certainly is easier than carbon dioxide, I would say.
Yeah. What if we don't do anything about methane? What if we let the leaks continue? How big an issue will that be, big picture, as it relates to climate change?
I can't quantify that. Clearly, there will be more global heating, there will be more greenhouse gas in the Earth's atmosphere, and temperatures will continue to rise, and sea level will continue to rise, probably at a faster rate.
So it's important, Rigo.
I think it's important.
Here's the thing. When most of us think about climate change, we get overwhelmed. It's a problem that's so big, we tend to just kind of throw our hands up, walk away. The default is apathy. And there's no question. When you start talking about tackling CO2, it's easy to get overwhelmed. It's a gargantuan task that involves fundamental changes to just about every aspect of our economy. Methane, on the other hand, is more potent, it's less long-lived, and really most importantly, it's most easy to manage given its sources. It's a narrower sector of our world, and it is, at the bottom line, something that is good for the bottom line. It is a marketable commodity, so there is incentive to control it outside of any governmental regulation. You can sell methane, and maybe that is one surefire way we can work at reducing its presence in our atmosphere. Check out our PBS NewsHour story on this. It details the efforts of the Jet Propulsion Laboratory to fly a spectroscopy device called Avarice over large swaths of California to identify methane sources. And we talked to the folks at Southern California Gas about what they're doing to try to make their system less leaky. You can find all of this at milesobrien.com. And while you're there, go ahead and sign up for our newsletter. You won't regret it. It's just one email a week. And it'll keep you up to date on what we're doing to cover the world of science and keep scientific facts alive. Do us a favor, rate and review this podcast. It will help us gain a little traction as we try to turn this into some kind of business. For now, it's been a fun and interesting way to dive a little deeper into our journalism. Thanks for listening to Miles to Go. I'm Miles O'Brien.